morning we had a good introduction regarding what are stars, and then related to the star development, what are neutron stars, not superstars, but in the field of high-energy physics or even in astrophysics, neutron stars are a part of superstars because people are all curious about that, and they would like to study more and more on that front. They would like to know more about it. So naturally, it makes it also a neutron star, a kind of superstar. So, and then how do we catch it? This is the way. I've just shown a cartoon that a man is trying to catch something, and we will see what this man is and what it is there in his hands. Maybe some guesses already you must have made. So we will be discussing about the big and advanced detectors and to catch these neutron stars. Okay, I'm from VCC, and this is this entire talk is related to the compressed organic matter collision matter experiments at FAIR, and we will see in a moment what all these things are. Okay, so the previous speaker in the morning, he gave you full idea about what neutron star is, so I will not go too much into the depth of it. So I will just remind you typically some of the parameters that this neutron star is typically about size of a city, something like 20 kilometers or so, and it weighs around 1 million times more than the whole of Earth. So these are the estimates. And technically, it is no longer a star. The previous speaker had also mentioned that. And it is a phase that some stars reach at the end of their existence. Okay, the gravitational force is just enough to keep all the neutrons rotating in kind of in form of a shell or something. Okay, if the gravitational force would have been large, then it would have turned into a black hole. Okay, so the previous stage is the neutron star for large stars. Okay, while small stars, when they explode, they don't form; they just form small fragments. They don't form the neutron star. How are they detected? Maybe you test that or not, but I can just brush upon a few of the main properties. So as we saw that this has intense gravitational force, which means light coming from there, from the neighborhood or from the vicinity, will be kind of bent. So the astrophysicists or they have kind of really done such experiments and have found the presence, okay, using the signals related to this. And then there is pulsars. In fact, the first neutron star was detected by Jocelyn Bell Burnell in 1967 and on the observation of pulsars. So what are pulsars? These are just these are enormous gravity and fast rotating objects, and then they stream electromagnetic radiations. Okay, so I see all of them are technically qualified to understand this, so I don't want to go into school level details and explain. And then this pulse, as it spins and then points towards the Earth, then you have rapid radio wave pulses by which you detect, and then you have the information about the neutron stars. Do you know how many neutron stars are there? It's about 100 million, and this estimate is based on the number of stars that have undergone supernova explosions. Okay, so something like 100 million neutron stars. This also makes the first case to understand deeper what is inside this and what are its properties. The densities, okay, the densities inside a neutron star far exceeds anything found here on Earth. The positively charged protons and the negatively charged electrons, as the previous speaker had also described in the morning, they basically these compose of atoms, and these are literally crushed together to form neutral neutrons, and that's the name. Okay, so when the neutron star comes, the name comes mainly from there. So what are we going to study? I mean, if I say that we would like to study more and more of the neutron star, so very much, and also when I say what are its properties, so what properties? So as a school, from school way of learning, we know properties of matter. Okay, so what do we know about that? So we know that it exists in three states: solid, liquid, or gaseous state, and then these states depend also on temperature, and then they also depend on pressure, because water, if it boils at 100 degrees Celsius, okay, so at normal pressure, if you go to mountains, then it boils at lower pressure. So these are very, very, very basic properties regarding state of matter. And in a very similar manner, in similar line of thinking, we really want to study the equation of state. This variation, this study of pressure, volume, and temperature forms a part of the equation of state. So we really want to study the equation of state of this high dense matter which exists in the neutron stars. That is one of our main interests, which we cannot normally do from these signals or those pulsars and those things which we have kind of detected. Okay? Not so precisely. Okay. So that means the question is, what happens right at the star's core where the density is highest? Okay? Do neutrons dissolve into kind of super dense elementary particle soup of freely moving quarks and gluons as predicted by physical models? We don't know. Okay? So this theory can be tested in an experiment in FAIR, which is known as CBM, which is compressed dynamic matter experiment. Okay? And this will create such highly compact matter on a tiny scale. So just few slides back, I said that the neutron star dimensions are like 20 kilometers or so. Okay? So but here in this experiment, we are going to create the neutron stars of the high dense matter very much similar to that in neutron star at a scale of like one nucleon. Okay? Very tiny scale. And how do we do this? We take two heavy nuclei, accelerate them, and collide them. So this is a, as we'll see, it's a fixed target experiment. So you have a target, and you have a highly accelerating nuclei which has a lot of energies. And the moment it bombards, then for a very tiny moment of time, there is enormous amount of energy which is deposited in the tiny volume. And the entire matter kind of gets compressed, okay, at those energies which we are talking about. Okay? So at that moment, for a very tiny moment, this tiny size of neutron star-like density matter is formed in such collisions. Okay? How do we then know about its presence? Okay, we have collided. So how do we know that such a thing has happened? So we come to the only clue about this transient happening can be given by the numerous particles that are formed in this collision. So the moment collision takes place, there is so much of energy dumped at that point, and then this energy is kind of given out in form of numerous particles and their energies. So our aim is to detect all these particles, their energies, and then extrapolate what may have happened at the collision point. Okay, so that's how the role of detectors come play a role. So can one create such a matter in the laboratory, as I said in the previous slide? Yes. And this is how we do, by colliding two heavy nuclei. How do we collide? So we need energy, which means we need accelerators. And this is the accelerator facility, or this is the particular accelerator in FAIR, which is Facility for Antiproton and Ion Research. This is a facility which is coming up in GSI, in Darmstadt, in Germany. Okay? So around 2025, this will be ready, and the first beam will be delivered. What is so unique about this accelerator facility? The uniqueness is in terms of these particles. You see, so many primary particles, the luminosity, the beam luminosity is so high. 10 power 12 per second, 10 power 10 per second, 3 to 10 power 13 per second. What's so special? That till today, no accelerator facility, or not till today, I mean, as of today, no accelerator facility can deliver such high intensity. So that is the uniqueness of the FAIR accelerator. Okay? Now, when we talk about compressed baryonic matter, we talk about the phase transition from normal nucleonic state to a state of coagulant plasma. This is what is predicted in such high dense environment to take place. So how do we express this in our high energy field? Or typically this is expressed in terms of temperature versus net baryon density, bit similar to what we talk about, temperature versus P or temperature versus V diagram in phase transition of water when we talk about. Okay, but here we talk in terms of temperature versus net baryon densities. What does this cartoon mean? Okay, I can, if the previous speakers explain, I can just cut short a little bit. So, which means that if we are operating in a energy range where we get some temperatures of this order, or in a region where the particle has had a maximum stopping, the nucleus has had a maximum stopping at the target, that region corresponds to kind of very high, but otherwise here moderate temperature, and this region is considered to be high net baryon density as compared to this region. Okay? So we at FAIR, we want to create a matter which has kind of moderate temperatures but very high net baryon densities, and this is in line with our expectation that that the environment kind of that exists in neutron star will be created in such collisions. How do we detect them? Through particles, as I said. But through particles, in which particles? The most abundant kind of ions, or what kind of particles? So, the medium which is formed, our aim is to determine the properties of the medium. Okay? So, this medium which is formed can be investigated by something called rare probes, and these are basically open charm and charmonia. Basically, this is gypsy and this is dimizone. This falls into the category of zoo of particles which exist in particulator group. But these are really the particles which we want to detect because they carry the information about the collision point. But then at these energies, the production cross section is very low. So you want to have large number of such collisions to get them in sufficient number. And to have a large number of collisions means you may think of running the experiment years together, or you can think of really increasing the intensity. So years together, maybe a couple of factors is fine, but if it is orders, then it doesn't help. Factors in terms of statistics, okay? So then, so this is where to detect the rare probes, the high intensity of the luminosity plays a big role, okay? And so these are the typical energies of the beam. So in the lab frame, you have something like 11 HeV for heavy ions for cis 100, and now cis 100 and cis 300 are nothing but two phases of development of this beam experiment. Okay, so in cis 100, it's our energy, maximum energy for heavy ions goes up to 11 HeV, while in cis 300, which comes later, we go to for heavy ions up to like 35 HeV. Okay? So, and then, so as I mentioned that these rare probes, what is their, these rare probes are basically, do they have a name? So basically they are electromagnetic radiations, and they, or they have these, not radiations, but basically the particles like, as I mentioned, gypsies or dimizone, and they carry the information, and when you do their mass reconstruction, then since they have passed through this matter which has created, they will undergo interactions with that matter and carry the message of the creation of matter. And they will, when you do the mass invariant mass reconstruction, you will find some kind of a broadening in the masses. This is one of the signals that such an object, such an exotic medium has formed in the collisions. Okay? And people have done simulations how the density, okay, develops with time. So I show here that this is the density, okay, and this is time. So you see it reaches about 1.5, okay, 1.5 in terms of 1.5 Fermi cube inverse. Normal nuclear matter has density of 0.15. So you see, it reaches about 10 times the normal nuclear matter density. Okay, this is from the simulations. And okay, so then this is the layout of the CBM experiment. Okay, this is the place inside this blue box. Here, over here, is the place where the target will be placed, and where exactly the place where this high density material will be created by the collision from the beam, which comes from this side. Okay, so the beam comes from here, it collides here, and the beam collides, then it creates innumerable particles which kind of pass through different detectors. Okay, and these are the main detectors in CBM. Okay, so there is a vortex detector, and then there is a silicon tracking station. So if I want to detect the particles, first thing which I need to know is momentum. This particular magnet, blue thing, provides the curvature to the tracks. And then there are silicon tracking chambers inside this, tracking stations inside this, which kind of interact with all these particles and have point messages. Okay, so they have hit information, and based on this hit information, you try to connect the curve, and from the curve, radius of curvature, you know already the magnetic field, you know what will be the momentum. So this way you determine the momentum of all the tracks. Okay, so this is the heart of the CBM experiment, the STS. But then only through STS is not enough. You need to really identify the particles. How do you identify the particles? It depends which particle you want to identify. So as I mentioned, that the dileptons, I don't know whether I mentioned this in one of the slides or not. So the dileptons, measuring dileptons is one of the core in the CBM experiment. And the dileptons have mainly two channels via electron, which is E plus and E minus, or via muons, which is E plus and E minus. Okay? Both of them are not simultaneously generated. A particle decays into one of these modes. Nature leaves the particle to choose at any point of time which mode to decay into. But over a large statistics, there are something called branching ratios, so it should obey the branching ratio of the decay of the particles. Okay? So this is just to give you a glimpse how the particles, after collision, this innumerable particle, this is again a simulation, but this innumerable particles, how they are kind of spread out in space, and you need to know the information of hits of all these particles. Okay? So and these are so close to the collision, you have so much high density of tracks there. You really need advanced detectors to track those particles there. So silicon does the job at the vertex part. Okay? So another detector which is upstream, which we saw here, is the TRD, which does some kind of pion electron identification. Okay, then there is this rich, which actually detects the electrons, but then there will be some pion contaminants. Okay, so these pion contaminants will go up further and will hit here in TRDs. By knowing the hits in TRDs, you can differentiate between electron and pion, and that way you can really remove the background of the pions in this rich detector. This is the way how you can detect the dielectrons using a rich detector. Now, to detect dimuons, you move this rich detector away and push this detector called muon chambers. Okay? India is involved in this particular detector in the development and installation of this detector, the muon chambers. So I will show you a detailed layout in one of the slides of these muon chambers. So they cannot do a simultaneous measurement. This rich has to be this huge structure. Okay, so this entire from this blue length is something like 2 meters or maybe 2.5 meters. Yeah, because from here to here, this part is around 2 meters. And then further up. So you can see the scale of 2 meters is like this much. And then it goes further up for other detectors, downstream detectors. So such large detectors are used in these experiments. And then there is, in the last you saw some detector, this huge thing, okay? This is time of flight detector, which measures the time of arrival of different particles in this plane, okay? And these are basically resistive, these consist of resistive plate chambers, and which have a very fast timing, and based on the time difference of the arrival, they can really identify the particles coming, okay? So this is being developed by Heidelberg and other groups in Germany. And you see the area, this is something 150 meters square, that is the area. And this has 150,000 channels. Now we come to our neon chamber, which India is involved in, okay? So as the collision takes place here, all kinds of particles, they move. I've just shown two here for semantic purpose. And then you need to detect the thermion tracks. There are innumerable tracks which are coming. How do you know which one is muonal, which one is not? So depending upon which particle you want to detect, for example, jet size, then you have some kind of a information from simulation that these have 3.1 GeV as its mass, and these will decay to large momentum tracks which can penetrate up to this point. So based on the trigger from these stations, you can, and then combining up with the tracking from this center, you can really form the tracks and then identify the muons. You use the muons, use their invariant mass reconstruction, because you don't know which muon is actually, which pair of muon is from the parent particle. So then you use the combinatorics of for momentum to get the mass peak. Okay? And based on this, you finally get the yield of the particular species which you're looking at. So this involves a lot of programming and a lot of computation. So India's responsibility in chamber is first, second, and since last 1 year, also the third and fourth station. So for the first two stations, because of these absorbers, carbon, iron, and all these things in this beginning, you have lot of conversions, and then there are a lot of secondary particles which are generated because of these absorbers. Why do we need this absorber? Because if you don't absorb these ions coming, then the entire thing, we cannot just detect the muons from that pipe. So by putting these two, you in fact end up increasing, but then in these 3-4 stations over here, you really have a very clean sample of hits from which you can really develop the tracks. Okay? So what does it mean? What do you want to say from here? So these two stations have high particle rate, which is kind of added up. Already we have very high intensity of particle interaction, so large number of particles coming per second, and then the secondaries which are generated in the observer, they add up to it, so you have high particle rate. So you want to build a detector which can cater to such high particle rates. Okay? And then when you go to third and fourth station, there also the rates are of the order of 50 kilohertz. So when I'm telling high, you should ask how high. So here something is of the order of 400 kilohertz per centimeter, while in the third it is 15 kilohertz, and in the fourth it is much lower, maybe factor of 5 lower. How much? 5? Factor 3 lower. Okay. So that is the rates which we from simulation obtain, and then we decide which detector to use. Okay. So these are the challenges I have kind of summarized here in this plot, that we have a build detector which can cater to 10 megahertz collision rate. Okay, 10 power 7 collisions per second are happening, and that many, and you just multiply by roughly 1,000, and that many particles are kind of emitted in a full forward region or large forward region. Okay. which results into something like 400.4 hit per centimeter square, or if you multiply by 10 megahertz, then it comes out to be 400 kilohertz per square centimeter. So in 1 square centimeter, you are getting rates of 300 or 400 kilohertz of particle tracks. Okay? So this not only talks about detector technology, you have also to think about the DAC, what kind of data acquisition system you are going to use to really collect such high rate of data and store it. Okay? Then in such heavy ion collisions, you have large neutron dose. So I just, by looking at detector technology in terms of rate, I cannot build the detector. I should know whether it is radiation resistant or not. We all know about radiation because when we hear about all this space travels and other things, we come across these words called radiation, because when you go up, there is so much of radiation. So it's not only harmful to us. If the radiation is really high, it is harmful to the detector components. We have to choose the detector components appropriately. Okay? And then, interesting thing is again, is because of these high rates, you have to use something called self-triggered mode of data acquisition. So, suppose when you do an experiment, so there is, when you know that some particle you are trying to kind of detect, so there is a trigger. Okay? Like in oscilloscope, you put something, right, and you put some source. Okay? The oscilloscope is kind of a self-triggered thing. So with one channel, yes, you can have a self-triggered system, which just randomly, the moment it is above the threshold, you set a level over there, and you just see the signals coming up like this. So you literally want to store this over here. Why you cannot do in kind of a triggered event? Because that takes time, and you entire game of having high interaction rate and velocity is lost. Our rare probes again will take a lot of time to be kind of discovered. But then if you have such self-triggered things, then you don't have a definition of an event, then how do you combine so many tracks to know which track belongs to which event, which collision? You cannot just combine one track in one collision to some other track in some other collision. So this is done via the timestamps of the hit. So you choose the hit location and give a condition of the timestamps that in this particular time domain, all these things should be together. Now that involves enormous, computational skills and algorithms to really get to the realistic part of event reconstruction. See, so you have a free streaming data, no information that an event has taken place, and you have to construct events out of that. Events means all hits on the full plane which have happened at the same time. Okay, so this is a big challenge in CDM. And so now this is just a plot to show the kind of density. I said that there are large radiation level. How large is what is shown here. I already said that it has to sustain 10 power 13 neutron equivalents. Okay? And then this is for neutron, that was for the hit density. Okay, so now this is just a demonstration how your typical signal will look like. So from using dynions, if I reconstruct some of the particles like phi and omega, and this is how they would come out to be in simulation. So in simulation, you put all kinds of realistic things, kind of resolution, time resolution, space resolution, and try to study how much would you finally be able to detect. And further up, you introduce the detector effects, and you learn the systematics. You introduce the systematics, and finally get your the ultimate result. So this is using muons, and this is using electrons. You can see that on the lower side here, the background is much less in muons as compared to electrons. So that is the advantage of the dynion way of detecting the electrons. So okay, this is again a demonstration plot of an invariant mass reconstruction. So as I mentioned that you do all kinds of combinatorics on the momentum, for momentum. So you get all kinds of combinational masses. Okay, so this is how you get, but then the right ones will peak at the right mass, and finally you can get the event reconstructed. Okay? So far, fine. So what do we want to, if we want to do this physics which we have just done. We have to build the right detector. Okay. So this is what kind of detector we would like to have in muon chambers. This is the mechanical layout of this detector. Okay. And I have already told you the main design criteria of what the detector should be. So you see in this one plane, there are 3 planes over here. Huh? So in this one plane, there are something like 32,000 channels, tiny portions. So there are 3 layers, which means 32,000 times 3, typically 1 million such hit points in this region. Okay? From just the first station of muon chamber. You saw that there were 6 stations. So we are talking about the first station at this moment. Second one also has similar numbers. Third one has rather bit of relaxed numbers. So why these numbers are important? Because you are talking about hits synchronization in time. You are talking about DAC, which will kind of handle all these data rates in a synchronized manner. Okay, so it's very important to know how many your bandwidth. So these numbers will give you the total number of channels which will be occupied in any given moment of time, and this will help us in selecting the right kind of bandwidth. Okay. So each of these trapezoids would look like this. While this is an AutoCAD design, this is a real detector. Okay. And what is inside this? Okay, so what you see here is these are electronics connections. Your readout electronics will be kind of connected at these sides. Okay, and then what is inside this trapezoid? The heart of this detector, which I have shown here for the first station of March, is a gem foil. What is a foil? What is this gem foil? We will see in a moment. This is what is gem. Gas electron multiplier. What it is? It's a 50 micron. Our hair is something like 60 to 100 microns. Okay. This is a 50 micron foil, and this is just zoomed here. Huh? And this has a 5 micron copper layer on top and bottom surface. So 50 micron membrane like this, and you have 5 micron on top and 5 micron on bottom. So double copper clad polyimide foil. Okay. What do you do with this foil? You kind of chemically etch holes, tiny holes of this order. These are diameters of something like 70 microns with a pitch of 140 microns. Okay. Why is it? Why do you want to have such a detector? What is so? Because this looks to be pretty complex. We want to have a uniform holes all throughout such large chamber of this tiny dimension which you cannot see from your eyes. Okay. So close up will give you the picture. It is like this because the etching is done. Okay, this is a double mask process. That is why you see a picture like this. But this is a typical picture. We see this 50 microns which is here. How does this work? Okay. You apply potential difference across the top and bottom surface of this foil. How much? Of the order of say 500 volts. 500 volts across this distance. This is how much? I said this thickness is how much? 50 microns. So 500 divided by 50 microns is like 10 power 5 kilovolt per centimeter. 100,000 kilovolt per centimeter. Why? This is the electric field inside these holes. Okay. So what does it mean? That if I have some charged particle which kind of enters the gas volume and knocks off a couple of electrons, and if I manage to guide these electrons towards these holes, then they will end up getting energized and knocking off more and more electrons in that path and creating an avalanche by the time they come out of this hole. What does it mean? It only means that from one electron I have now many electrons. So I can do another thing. I can put another layer just below it, and it multiplies or amplifies further. And I can do another one, say third one, it amplifies further. So finally what I've got from one electron, I've launched from 3 layers a large amount of charge. This charge, if I kind of trap into some anode, or which is kept below over here, so it will show a current, it will show a pulse, and it will give me the information about the passage of this charge particle through the detector. Okay? So this is the pictorial view. So you see this blue line, high energy particle. Whenever in high energy we are talking about particle tracks, they don't stop. Unless we are talking about calorimeter, they just don't stop. They just pass through a detector. Okay? And then they interact. Now our goal is to exploit this interaction to the level of obtaining a signal. So these particles will generate some kind of primary electrons in this drift region. And this gap is something like 3 millimeters. These electrons, as I mentioned, this is a cathode here, so these electrons are guided toward the holes by this cathode, which these electrons over here are then amplified, as I mentioned in the previous over here, which are then further amplified in the second layer, and then further kind of multiplied in this third layer, and finally you see a collection. Okay? So this is how what has happened is that inside gas, one electron has multiplied into many one, and that is why the name gas electron multiplier or GEM detector. Okay? So GEM detectors have a lot of potentials in X-ray imaging and medical imaging. We will see in cases like that. In fact, a lot of some aspects of this will be discussed in one of the talks by Cycle in the next few days. Okay. So after showing you this last final piece, I would certainly go through how this development was carried out at VCC, where we are doing this work on this muon chamber. VCC leads the muon chamber development in the country. Okay, and so we started with 10 by 10 prototype, just this much, which is there in the fair exhibition, if you have seen that. And then we assembled it in lab like this. We have a radioactive source, we got signals, okay? And then from 10 by 10, we moved to 30 by 30. So you see, these foils, you get these foils as a raw material. Raw material means with holes, of course, yes. Now you have to have a tightness of this membrane. So there are ways we did something called thermal etching, okay? Because we have to maintain a gap of 1 to 2 millimeters between any two planes. Not only for this one, but even for large ones. Should not have any sag like this. The moment you have a sag, the fields are different. Your signal is different. You get some charge over here, some other charge over here for the same particle. You cannot afford to do that. Okay, so there is a lot of optimization or a lot of investigation and technical issues involved when you build such a detector. So this is just a schematic to show that how the detector is connected to the DAC. So this detector is connected to a cell-triggered electronics, which is the NX cycle, and then to some kind of readout controller, and then we have a DAC, which is specialized DAC, and then it goes to PC. And this you see we are kind of building we have just built it and we are just testing or assembling this large size triple chamber. Okay, 3 such membranes in such large one. Okay, how do we do it? I'll show it in a moment. So this is one such picture for some beam test. We were trying to do it in this center. And then we tested such a thing in one of the particle beam lines in Cozy, in Jülich, in Germany. And we got signals like this from 10 by 10. We saw the beam spot on the 10 by 10 module and also from the 30 by 30 chamber. Then we go to building. Okay, I've already shown you one laser chamber. And if I zoom it further into that detector, so I see these are the readout paths. So I mentioned in one of the slides that we have 32,000, right? So I calculated this from 69, something like 2,000 per module, and in this we have 2,000 of them. And thing to notice over here is you can see this, the pad sizes are small and this is large. So we have to, why is it like this? Because when the collision takes place, particles emerge from the collision point in a conical manner. So very close to the beam point, you have high density of particles for the same area, as compared to when you go away from the beam point. So I cannot do with such big sizes. Then I have several tracks which pass into one particular pad, and I don't have information then for this multi-track. So I have to go to very, very small size of granularity. Why do I need to do this? Okay, two track. I mean to say we have segmented into very small portions. Why do I need to vary it? I can keep the same all throughout, right? But if I keep the same, then you see so many pads, okay? So much of electronics, so much of kind of economic constraint over here. Electronics are extremely expensive. So when we design a detector, we have to think even in this direction that if we can minimize it, that will be better. Okay, so this way, this granularity, who chose this? How do we choose this size? This is done in simulation by knowing the total particle density and then the occupancy, considering also the data bandwidth and everything. Okay, so that is how these things are optimized. And this is a 8-layer PCB designed in BCC, fabricated in India, in Bangalore. Why I say 8-layer? Because tracks are so close by, you cannot just take it onto surface, just one surface. So you have to have multi-layer, multi-layers to pass on the track with insulation in between them. So in a total thickness of something like 2.5 millimeter, there are 8 layers. Okay, so this technology is not so much available with many industries in the country. Okay, so this is the large size detector development at VCC. You are already seeing the foils. This is how the readout drift and the readout PCB looks like. What is the drift one? The top one which guides the primary electron towards the kind of the holes. Okay, and then how do we stretch it? Okay, so these are some kind of spacers. We would like to also stretch it further. So this is the way we stretch it. We have these foils here. These are the spacers. We put one spacer like this. We put the spacer here. We put another foil like this. We put a spacer here, another foil, and in the end, we put some screws like this on top of each one. Okay, you see this. So we put the screws so as to clamp all these 3 foils together, and then you just kind of push it. How much minutes I have? 2 minutes. Okay. So you clamp this together, and later on you can see in one of the slides, you can see here that you tighten it all throughout, okay, and then you stretch it. So this has been developed by the high energy community. We have used this technique to the sizes, to the foils or the detector dimensions which we have designed. Okay. And then this is one of the main places which I have already mentioned. I must mention here this slide because finally how your detector behaves. How do you measure whether it satisfies all the design criteria? So this is the pulse height spectra, which is very close to Landau. I don't know if you get this, what it means. And then main thing which I think you can easily understand is that if I shoot 1,000 particles, do I detect all 1,000? Or I detect only 50%. This particular efficiency tells me about 95%. Then I detect 95% of these tracks, which satisfies one of the main design criteria. Okay, and this is the time correlation spectra, and this is just how much pads it occupies. One track, one charge particle occupies in the vicinity. So this is the cluster size. Okay, so I have already mentioned this. So this is the first station, but then we have to build the third and fourth station also, which will be. So I have discussed only about the first 2 stations, detector for the first 2 stations of much. There are developments going on for the third and fourth, which involve reciprocating chambers, which I because of time constraint I did not include. So, what do we learn? That advanced detectors, by the signal collaboration, would be able to get the picture of this high dense matter in a fleeting manner, but yes, we should be able to do this. Okay? Before I end, such detectors also have lots of spin-offs, means other uses, other applications, which I mentioned in one of the slides. And the spin-offs are, which we have demonstrated at VCC. We did X-ray imaging using triple gems. This is our detector arrangement setup in VCC. And then we got such images. We put some angular ring like this, and we got images from triple gem detector. Okay, these are strip detector, not the bad one, but they involved gems. So in India, this is the first such attempt using gem detectors and imaging using gem detectors. And but you see, the point to note is all these things could be done because of advanced electronics, the self-triggered electronics. It also needs advanced DAC, which comes up to read this free streaming data. And then you need a smart event algorithm, event building algorithm, based on the timestamps that you can really group the hits into an event, and only you can get these kind of images, right? If it crosses over, then you just are lost. Which hit belongs to which place? Okay? And further on, we did a fishbone with imaging. We just put a fishbone below here on the triple gem chamber, put an X-ray source here, and use the same data acquisition system, and this is the image of this fishbone which you get. That's the spin-off part. So advanced detector not only help us in this thing, but also the spin-offs. Thank you. Questions?
Thank you, Dr. Buller, for your nice talk. So now we will open for questions.
He answered one good point. These are the two things we are looking for.
True. In the first slide, I purposely did not write. So, yes. The story was so nice that everyone fell asleep.
Actually, everyone was lying. It was very quickly looking at all the things. Yes, when it is so nicely demonstrated.
Okay, thanks. No questions?
But your explanation was fantastic.
Any slide, any confusion? You may not have remembered some questions, but if any confusion, I can go back to that slide. No, he can give me a couple of minutes. No? Okay.
Okay, so